In this video, we're computing the period of oscillation for a thin ring physical pendulum. So we've given this thing a mass of m equals 1.5 kilograms and a radius of 20 centimeters. And we just set it on a pin and release it from rest up at an angle, and it just wiggles back and forth like this. Now we're going to bring in a couple key results from previous videos. First, we've already derived the period of a physical pendulum, and it turns out to be 2 pi times the square root of I over mgr center of mass. Now that I is the moment of inertia of the physical pendulum about the actual rotation axis. In other words, using the pin at the edge of the ring as the rotation axis. M, of course, is the mass of the ring. G is the acceleration of gravity, and R center of mass is the distance between the rotation axis and the center of mass of the physical pendulum. And the center of mass of this physical pendulum is just the center of the ring. And I'll post a link to the video where that result was first derived. Second, we need the parallel axis theorem. And that says if we know the moment of inertia of an object about its center of mass. So that's about right there. And we do have a formula for that we derived previously. Then we can find the moment of inertia around a parallel axis. And that, of course, is the location of our pin that we're actually rotating around by taking that moment of inertia about the center of mass and then tacking on a term that looks like mr squared, where r is the distance between the two parallel axes. In other words, it's going to be the same thing as r center of mass, the distance between the pin and the center of mass of the ring. And of course, I'll post a link to the video where that theorem was derived as well. So we can put all this stuff together pretty quickly. First, we're going to find the moment of inertia for this ring about the pin that it's actually rotating around. And again, we're going to use the parallel axis theorem for that. So I start with the moment of inertia about the center of mass, and then I tack on this term, mr center of mass squared, where that little r center of mass is the distance between the axis we're actually rotating around and the center of mass of the ring. So now we need to recall the moment of inertia of a thin ring about its center of mass. That turned out to be mr squared. And I'll post a link to the video where that was derived. And then our second term from the parallel axis theorem is just another mr squared because we're using a big R for the radius of the ring. So we find out that our moment of inertia is 2 mr squared. Now we're ready to plug into the period formula for a physical pendulum, and we replace I with 2 mr squared. And notice that our masses are going to cancel out here. I have an m in the denominator as well. And again, that r center of mass is just big R in the diagram. So a factor of r cancels out as well, and we arrive at a symbolic solution for the period. And that turns out to be 2 pi square root of 2r divided by g. So again, it's interesting to note that that period is independent of the mass of the ring. And now we're ready to plug some numbers in and find out just a numerical result for this particular ring. And we plug in our radius in SI base units. That's a 0.2 meters. And then for g, we'll use about 9.8 meters per second squared. And when I run the numbers on this to 3 significant digits, I find a period of oscillation of 1.27 seconds. And we're done.